There is this really distinct feeling when you switch from a language like Python or Java over to C. It's not just a change in syntax or, where you put the semicolons. It feels like you've been driving a Tesla with autopilot, and suddenly someone tosses you the keys to a 1960s muscle car.
Oh, yeah. Manual transmission, no power steering, no anti-lock brakes. You feel every single bump in the road.
Exactly. And if you don't know exactly what's happening under the hood, if you don't know how those gears mesh together, you aren't going anywhere. You're just going to stall out right there in the driveway.
Or worse, you just strip the gears entirely. And I mean, in this analogy, the gears are your computer's memory.
Right, which is the perfect setup for today's deep dive. We are looking at the Class 12 notes for CS330, and frankly, we are looking at the bare metal of the machine here. This is the inflection point in the course where we have to stop just writing code and actually start managing memory.
Yeah, we're talking about the relationship between arrays and pointers, the illusion of strings, and that invisible step called the preprocessor.
And looking at the syllabus, this is landing right as things get really heavy with Lab 4. So the mission for today is pretty simple. We need to decode this memory manual so you don't crash the car.
I like that. Let's get right into it.
So I want to start with a concept from the slides that actually made me stop and think. It was just a header on a slide, but it felt kind of profound. It just said, no strings.
It's a bit of a shock to the system, isn't it?
It really is, because in almost every modern language, a string is a fundamental object. You type a quote, you write hello world, you close the quote, and you're done. The computer handles the storage, the length, everything. But you're telling me C, like the grandfather of these languages, doesn't actually have a string data type.
Technically, no. C has no native string class or type at all. What it has are arrays of characters. It's a subtle distinction, but it changes pretty much everything about how you write your code.
So when I write the word hello in C, I'm not creating a single text object. I'm reserving a block of memory and placing HELLO into little adjacent boxes.
Precisely. It's just a sequence of bytes stored side by side. And this brings us to the most dangerous part of C strings. Since it's just a raw list of characters, the computer has no inherent way of knowing where the word ends.
Right, because in Python, the string object stores its own lengths. It effectively says, hey, I am 5 characters long.
Exactly. But in C, memory is just one long tape. If you have an array of size 100, but you only write the word hi, just 2 letters into it, the computer looks at that memory block and sees 100 slots. It doesn't know that only the first 2 matter. It just sees data.
Unless we use the flag.
Yes, the null terminator.
The famous \0.
Think of it as a sentinel standing guard. You write H, I, and then immediately after, you absolutely must place this special 0 byte. That tells any function reading the array to stop right there because the message is done.
The notes actually mention a specific bug called the missing \0. It sounds so trivial, forgetting one invisible character, but the consequences described in the slides they're pretty chaotic.
Oh, it's a classic memory error.
Yeah.
Let's say you manually build a string character by character, maybe in a loop, but you forget to tack on that terminator at the end. When you ask the program to print that string, it starts at the beginning and just keeps printing.
It doesn't stop at the end of the word.
It can't stop.
Yeah.
It has no idea where the end is. So it prints your word, but then it keeps marching through memory, printing whatever garbage data happens to be sitting in the next RAM slots.
So you get like smiley faces, random symbols, maybe pieces of other variables.
Right. Until it hits a 0 by pure chance, or this is more likely, until it tries to read memory it doesn't own, and the operating system steps in and kills the program with a segfault.
Wow. It really highlights that in C, you are the garbage collector. You are the manager. The compiler isn't going to save you from yourself here.
No. It assumes you know exactly what you're doing. And that philosophy is really evident in the longest line program from the notes.
Yeah, I looked at that code. It's designed to read user input and remember the longest line of text it encounters. In a high-level language, if I wanted to save the longest line, I'd just say longest equals current. Just a simple assignment.
And in C, that exact line of code would throw a compiler error. You cannot assign one array to another with an equal sign.
Why is that, though? If they are both arrays of the exact same type, why can't I just copy them over?
Because in C, an array name isn't the data itself. It's actually a pointer to where the data starts. If you tried array 1 equals array 2, you aren't copying the text. You'd be trying to overwrite the address of the first array with the address of the second.
Ah, so you have to physically move the data.
Byte by byte. The longest line program uses a helper function called copy. It loops through the source array, picks up a character, puts it in the destination array, moves to the next slot, and just repeats that.
Until it hits the null terminator.
Exactly. It always comes back to the terminator. If that function doesn't see the \0, it'll just copy forever or until your program crashes.
Okay, so we have this very manual memory management for strings. But before the compiler even turns that code into a program, there's another step involved. The notes call it the code before the code, the preprocessor.
This is a part of the compilation pipeline that is pretty unique to C and C++ tree. Before the compiler even looks at your syntax, the preprocessor runs through your text file and performs edits.
It's basically a glorified text editor running inside the build process.
That's a really great way to put it. It looks for lines starting with a hash symbol, like #include or #define.
Let's talk about #include. We use it constantly, right? Like #include stadio.h. I always assumed it just told the compiler, hey, I need the standard input-output library.
It's actually much more literal than that. When the preprocessor sees #include stadio.h, it goes to the system folder, finds the file name stadio.h, copies every single line of text from inside it, and pastes it directly into your file, completely replacing the #include line.
So my tiny 20-line program might actually be 2,000 lines by the time the compiler actually sees it?
Easily. It expands significantly. And the slides make a key distinction here about the brackets. You notice we use angle brackets for standard stuff, but quotes for other things.
Right, like #include, quote, myheader.h, unquote.
The quotes tell the preprocessor to look in the current directory first. It means this is one of your files. The angle brackets say, don't bother looking here, go straight to the system library folders.
That's a really practical tip for anyone debugging their own header files, but the real gotcha in the preprocessor section seems to be macros, the #define directive.
Yeah, #define is powerful but dangerous. On the surface, it's just a find and replace tool. If you write #define max 1000, the preprocessor just swaps every instance of the word max for 1000. That's safe. That's just a constant.
But then you have macros that take arguments. They look exactly like functions. The slide has one that's amax parenthesis a comma b.
They look like functions, but they absolutely do not behave like them. Remember, this is text replacement, not value calculation. If you define a macro to find the maximum of two numbers, it literally pastes the logic, the greater than comparisons, into your code wherever you use it.
The notes have a very specific warning that says macros are not statements. Why does that matter in practice?
Because of semicolons.
Yeah.
It's muscle memory for us to put a semicolon at the end of a line. But if you define a macro and accidentally include a semicolon in the definition,
it pastes the semicolon into the code too.
Exactly. Imagine you use that macro inside an if statement. The preprocessor pastes your code, including that extra semicolon. That semicolon might signal the end of the if block prematurely. Suddenly your else statement has no matching if, and your code won't compile. Or worse, it compiles, but the logic is silently broken.
That is insidious.
It really is. And there are side effects too. If you pass something like I++ into a macro, and that macro uses the argument twice in its text replacement, you might end up incrementing I twice without realizing it.
So the takeaway seems to be use macros sparingly.
Yes. They are great for constants, but for logic, modern C compilers are smart enough to optimize real functions. You rarely need the risk of a complex macro.
However, there is one preprocessor feature that seems totally indispensable: conditional compilation, the #ifdef tag.
Oh, absolutely. #ifdef stands for if defined. It allows you to wrap chunks of code so they only exist if a certain condition is met.
The optional .c file in the notes demonstrates this. It's basically turning variables on and off.
Think about cross-platform development. If you are writing a program that needs to run on both Windows and Linux, those operating systems handle things like file paths very differently.
So I can't write one code block for both.
Not always. So you write a block wrapped in #ifdef Windows and another in #ifdef LinyX. When you compile on Windows, the Linux code is stripped out completely before the compiler even sees it. It keeps the final binary clean and efficient.
It's fascinating how much control you have before the code even runs. But let's move to the main event here. The topic that makes every computer science student sweat: pointers.
The infamous pointers.
The slides define a pointer as a variable that contains the address of another variable. That sounds simple on paper, but I feel like the reality trips everyone up.
I think people overcomplicate it. Let's look at the memory diagram in the slides. Memory is just a long street of houses. Every house has a number and address.
Okay, I'm with you.
If you have a variable x equals 50, that means inside one of those houses, the number 50 is sitting on the couch.
Right.
A pointer P is just a slip of paper with the address of that house written on it. It doesn't hold the number 50, it holds the address, let's say, 1000 Main Street.
And we have two tools to handle this slip of paper, the ampersand and the asterisk.
The ampersand is the address of operator. P equals ampersand X literally translates to find out where X lives and write that address on my slip of paper P.
And the asterisk, that's the dereference operator.
Correct. If I write asterisk P, I'm saying don't look at the slip of paper. Go to the address written on the paper, look inside the house, and tell me what you see.
This is where the power comes in, because if I write asterisk P equals 100, I'm not changing the address on the slip of paper. I'm teleporting to that house and changing the furniture inside.
You're remotely controlling the variable X through the pointer P.
Now here is where the class notes drop the real bombshell. We talked about arrays earlier. We talked about pointers just now. The slides say they are the exact same thing.
Deep down, yes. This is the big aha moment for C programmers. When you declare an array, say into bracket 10, the variable A is really just a constant pointer to the first element.
So A is perfectly equal to ampersand of bracket 0.
Yes. And this unlocks pointer arithmetic.
This was the math part that confused me initially. If P is an address, say 1000, and I do P plus 1. In normal math, that's 1001, but in C...
In C, it depends entirely on what P points to. If P points to an integer, and an integer takes up 4 bytes of space, then P plus 1 actually adds 4 to the address. It becomes 1004.
It's smart scaling. It doesn't move forward by 1 byte. It moves forward by 1 item.
Exactly. It moves to the next house on the block, regardless of how big the house actually is. And this reveals the secret of array indexing.
You mean a bracket I syntax?
Yes. When you write a bracket I, the compiler secretly rewrites that as asterisk parenthesis A plus I.
Let me parse that. It takes the starting address A, it does the pointer math to jump forward I steps, and then the star dereferences it to grab the value inside.
That's it. A bracket I is just syntactic sugar. It's a pretty shorthand for pointer arithmetic.
That perfectly explains why arrays strictly start at 0.
Right. Asterisk parenthesis A plus 0 means start at a byte and move 0 steps. If arrays started at 1, the math would be messier. You'd have to subtract 1 every single time. C prefers raw efficiency over human counting.
This duality that arrays are just pointers explains why passing arrays to functions is so fast. In other languages, passing a huge list might involve copying the whole list into the function,
which is slow and wastes a ton of memory. In C, when you pass an array to a function, you are literally just passing that one address, that single slip of paper. The function now knows where the data lives and can access it directly without copying a single byte.
But that brings us right back to safety. If the function has the address, it can change the original data.
It can, and it will. This is why C is technically referred to as pass by value, but when that value is an address, it behaves exactly like pass by reference. You are giving the function the keys to your house.
Okay, so we've established that strings are arrays and arrays are pointers. This circles us back to the standard libraries. Since C doesn't help us with strings natively, we have to use string.h.
Right. We mentioned Strolman for length. And remember, it counts the letters excluding the null terminator. So the word hi returns length 2, even though it occupies 3 bytes of memory.
And then there's stretchapy for copying.
Be incredibly careful with stripey. It assumes the destination array is big enough. If you try to copy a 50-character sentence into a 10-character array, Stripey won't complain. It will just blast through the memory boundaries, overwriting whatever variables came after your array. This is the literal definition of a buffer overflow exploit.
Wow, so always check your sizes. What about string compare?
This one trips people up constantly. It compares strings lexicographically, basically alphabetical order. But look at the return value. If the strings are identical, it returns 0.
Which is the exact opposite of what you expect. Usually in Boolean logic, 1 is true and 0 is false. Here, 0 means success, they match.
Think of it as 0 difference. If it returns a negative number, the first string comes before the second, alphabetically. Positive means after.
Got it. Before we wrap up the technical side of this deep dive, there's one more advanced structure in the notes. Arrays of pointers, or vectors.
This is distinct from a 2D array. If you make a standard 2D array like char table 5x10, you are building a perfect grid. 5 rows, and every single row is exactly 10 bytes wide.
Even if the word inside is only hi.
Yes, you waste the other 8 bytes. It's a rigid rectangle. But an array of pointers is different. It's a ragged array.
Ragged how?
Imagine a vertical array where every slot holds a pointer. The first pointer points to a tiny string like hi. The second pointer points to a huge paragraph somewhere else. The third points to a medium word.
So the rows can be totally different lengths.
Exactly. You only allocate exactly the memory you need for each string. It's much more memory efficient, especially for lists of words like a dictionary, where lengths vary wildly.
That sounds a lot like argy. The arguments to main works exactly this way.
That is exactly what argive is.
Yeah.
Char, star, argy, bracket, bracket. It's an array of pointers to the strings typed in the command line.
But it adds a layer of complexity. You have to manage the memory for every single row individually.
That's the trade-off. Efficiency versus complexity. That is the C language in a nutshell.
Speaking of complexity, we need to look at the workload for the students. This is a heavy week according to the syllabus.
It really is. We are looking at Lab 4, which is Lab 4C, arrays, and pointers.
So you know the drill. Go to your individual lab work directory. Use git pull to get the latest assignment.
Inside, you've got the examples we discussed today, pointer1.c, char copy 1.c. Don't just read them. Run them. Break them. Remove a null terminator and see what happens on your machine. The instructions are to explore these and then create your own programs.
And the deadlines are tight. Lab 3, the B- scanner, was due Monday the 23rd. If you are listening to this and haven't submitted it, stop what you're doing and go submit it.
Definitely prioritize that. But looking forward to Friday, February 27th, there's reading, Chapter 5 in the compiler's book.
And a very relevant article for anyone doing a deep dive on this stuff. Developer survey shows trust in AI coding tools is falling. This is from Stack Overflow.
This ties in perfectly with our topic today. AI tools are great at generating Python boilerplate. But when it comes to C memory management, pointers, and subtle off-by-one errors, they struggle.
I've seen that firsthand. You ask an AI to write a C-string function, and half the time it forgets to allocate space for the null terminator.
Exactly. That's why you need to learn this stuff manually. You need to be able to audit the code the AI gives you. You can't fix a seg fault if you don't understand the underlying memory model.
Then, Sunday, March 1st, journal entry for week 6.
The 2-1 rule. 2 paragraphs of reflection, 1 quiz question. Do not forget the quiz question. It's free points, or free points lost if you forget it.
And finally, next Monday, March 2nd, Lab 4, the Pointers Lab, is officially due.
It's a gauntlet of a week. Manage your time well.
I want to leave everyone with a thought to chew on while they're debugging. We talked about the longest line program and passing arrays.
Right.
In Intro to CS, they always teach us that global variables are evil. They create messy dependencies. They say always use local variables and pass parameters.
That is the standard advice, yeah.
Yeah.
It keeps functions clean and isolated.
But we just learned that in C, passing an array is passing a pointer. And a pointer allows the function to modify the original data directly.
Yes. It creates a side effect. The function can change the state of the program entirely outside of its own scope.
So if I can reach through a pointer and change a variable in main from a completely different function, doesn't that effectively make that data global?
It really blurs the line, doesn't it? When you have the address, distance implies nothing. You can be in a different function, a different file even, but if you have the pointer, you have absolute control.
It changes how you think about scope. It's not just about where the variable lives. It's about who actually holds the map to find it.
And more importantly, who you trust with that map.
Good luck with the pointers, everyone. Keep those null terminators handy.
Happy coding.